Welcome to, I think it's 21st edition of Global Elixir Meetup, and we've had like 21 stream behind, which is really cool, and I think the initiative is amazing, and it all came up in a big chunk because of amazing work done by Software Mention and developers behind Software Mention, so I think they deserve a round of applause for doing that. Really cool. And today I'll speak about Torus and actually about search. So all applications work around the data, and it's essential to, for them to serve this data in efficient and relevant way. And what is a better way of serving the data than letting the users to search through the data, right? So the Torus library focuses on letting you as a developer implement in a really easy way most of search types that you would probably need in your app. And you can do that in a single line of code, and I'll promise I'll show you how to do that. Also, Torus has an amazing documentation about all these search types and where to pick which search type. So you don't need to memorize everything I tell you today. You can just visit Torus documentation and you will be able to find probably anything you want there. So first, let me start with a little introduction to gain some value in your eyes, probably. So my name is Dima. I work as a software engineer at Software Mention. I've spent almost 4 years working in Elixir. I've started my career with doing some machine learning in Python. I've actually did some recommendation algorithms for literacy portals. It was kind of Spotify for the books, where you fed the books the users read, and it actually outputted the books for them they might like. And then I joined Software Mention, and I've been working on Membrane, which probably most of you are familiar with, which is a multimedia platform. And then I've joined a United States-based company as a contractor, and I've been working there primarily with Elixir for more than 3 years. So regarding the search, let's build an app so we have an example we can derive our things from, and we can actually have some problems to solve, because I think that if we don't have problems, then we don't need to do anything, right? So our app will be focusing on managing conference talk submissions, but from the organizer side. So our main functionality will be to view, accept, or reject the submissions, or see all submissions. And the first problem we might want to solve is to be able to search by phone number. Phone numbers have this property that semantics of the data live in the characters of the data. Because if you type 1, then there is no chance, or there is really low chance that you meant 2, and only because it's a close on the keyboard. And for phone numbers, we use pattern matching search. So pattern matching searches for a specific pattern in a string. And we have in PostgreSQL, so assuming that most of you use Ecto, Elixir, and Postgres stack, in Postgres we have 3 options for pattern matching. We have like, I like, and similar to. They all differ a little, but they are kind of focused on pattern matching search. And we use pattern matching for when semantics of the data live in the characters of the data. And in SQL, there is a relatively easy way to implement pattern matching. So for example, like coming back to our previous application where we needed to search by phone number, we can implement that relatively easily using just similar to operator and passing the term. Probably we might want to also include some country code, like here. And in Ecto, you would do something like that. So you will have your user. Unfortunately, there is no way in Ecto to single-linedly use similar to expression. So you would need to fall back to fragments. And in this case, that would look something like that. And here comes Torus, where you can actually use Torus similar to, implying that it is similar to, right? Then you pass binding. Then you pass columns that you want to search through, and you pass your term. So this term can be a variable, right? And in this particular example, it is not super helpful because we've kind of reduced only 2 lines of code. But going forward, you will see that we will be able to replace huge amounts of code with just a single abstraction, which is kind of isolated, kind of easy to use, and definitely is well documented. So, and also, the benefit of Ecto, which probably you are all familiar with, is that you can compose, the composability of Ecto. You can compose your queries, you can stack them, you can derive different logic to different parts of the app, and because of that, you can actually abstract away some parts and make your queries look cool. And this is actually what Torus does also. Like in this example, your complex logic can be abstracted away. So the second problem that we want to solve is searching by first and last name. We can't use pattern matching here because you probably can do typos in names, right? And we probably want to catch them, and we probably want to return something back. And for actually catching typos in short text fields, there is a similarity search. So similarity search searches for records that closely match the input text, and it uses trigram distance. Trigram distance works by splitting the word or the sentence into trigrams. Trigrams are sets of 1, 2, or 3 characters. Then they are compared together, whichever, the amount of matches is compared, and in percents they're compared, and then you have a score from 0 to 1. So 1 means exactly all characters, all trigrams match. This is how similarity search works. And in Postgres, we have 3 options for similarity search. We have similarity, word similarity, and strict word similarity, and they all differ by the strictness on how your word is compared in the sentence. So the stricter we are, the less errors we will catch in the sentences. So we use similarity search to fuzzy match and catch typos in short text fields, like full name. And in Ecto, actually I won't provide you an example in Ecto raw because it is too complex. I will dive deep into the Torus. So in Torus, you could use similar to actually or I like, or similar to. You pass bindings, column names, and then a term. Also, every single function in Torus library has options derived from the Postgres, from Postgres functions. So you could use them. And also, they do add some overhead to the implementation from Postgres. And for example, in this particular case, you could pre-filter the results. And pre-filtering is fast because you don't need to go through all of them. You could use some indexes, which derives from the way Postgres stores this data, right? And you can pre-filter them, or you cannot. And also, I've picked by default some opinionated defaults for you, so you could actually do something like that, and it will also return reasonable results. And it's, again, a single line of code. So in this example, we are inserting a few users, and then we can search them with a typo, and actually, it works. So we got returned two examples. Then imagine that we have our suggestions, conference suggestions, and we want to search by the body of the suggestion, and maybe the title. So we want to actually, for example, validate if we don't have similar suggestion already suggested, right? So in this case, we have a long text, so it's not reasonable to use similarity search because similarity works best on short strings. And to to solve this problem, we have full text search. So full text search finds strings that contain these particular terms. It does not tolerate typos, but we don't care about them because we can kind of ignore the factors that don't match. It supports prefix search, so we can actually prefix search our long chunk of data, which is really cool. And it works so we have a sentence, then we remove stop words from the sentence, so the words that do not bring any value to the meaning of the sentence. Then we stem them to the lexems, So we bring the word into their like first form, into the initial form. Then we vectorize them. So we create vectors out of these words. So we append the position of the word in the sentence. So this is also included in the ranking. And then we just compare the vectors, right? So the closer these two vectors are, the probability that these two terms are close to each other and are the same is bigger, and because of that we return the word. And it actually works really cool. So probably if you open a PDF document and search something there, you will use under the hood full text search. And if you try to find something with typo, this won't work because full text search won't tolerate typos. But prefix search will work. So this is the thing. And we use full text search when we don't care about spelling, the documents are long, and you need to order the results by how close they match what you've inputted. And in Torus, implementing full text search is not easy. So if any of you have done that, you probably know that this will require maybe bringing the whole module with you, because there are different steps of full text search. And what Torus gives you is you can, again, in a single line of code, implement full text search, pass all the columns that you need this full text search to be searched through, and pass the term, and it will just work. Also, full text search works best if you have your things that you search through stored inside a vectorized column in your Postgres. And Torus also supports that case. So for that case, you just pass stored true, and then you pass the vector. And it will be blazingly fast, because searching and comparing vectors is blazingly fast, right? But this has some issue. So the problem there is that we don't understand the meaning behind words. So we only match the words, but not their synonyms. What if we want clever suggestions, buddies? What if we want to have clever search? And to have clever search, we have semantic search. Semantic search understands the meaning behind words, and it uses embedding vectors to do that. So embedding vector is a vector representing the meaning of the word in a high-dimensional space. And the closer two vectors are, this probably means that they mean the same thing, right? So yeah, so you can use synonyms in this search. And it works by, you need to vectorize, you need to create embeddings for your data first, and then you need to create embeddings for your term, and then you compare these two together. So you compare your embedding with every embedding for the rows in your database, and then if it's a match, if they are close, they are ordered they are prioritized and returned first. And the caveat here is the more dimensions vector has, the more information it can capture, but then it is harder to compare them. And the lesser information you have, the easier it is to generate an embedding. And I'll show you an example later on that you can generate embeddings on the client, which is really cool because you don't need to have the compute power in your server, and you can delegate generating embeddings to the clients. And we use semantic search really carefully when we need to understand the intent, handle synonyms, and we are okay with being a little slower in comparison to full text search because we need to vectorize your query. We need to create an embedding, an embedded vector. And again, in Torus, it is almost a single line of code. So all you need to do is you need to use a function Torus to vector to convert your term to the embedding vector. And then you need to compare your existing embedding vectors, which you've also created using Torus to vector or to vectors function, with this newly created embedding vector. And then your results will be automatically ordered by the score, by how close these two vectors are. And you might be thinking, how do we generate these embeddings? And that's a really great question because the core of semantic search is not comparing vectors, it is generating these embeddings. And Torus kind of has your back here because it is super extensible on the way you can generate embeddings. So the one of the options might be to use some third-party APIs. For example, like Hugging Face, OpenAI, Gemini. And for all these three, it is really easy because Torus already has modules to do that. So you only provide the keys, and Torus will generate the embedding for you and will create an API to do that. But maybe you might want to generate them yourselves. And if you want to generate embeddings yourselves, then you have an option to use, for example, PostgreSML. PostgreSML is a Postgres extension that it is a version of Postgres, which has Python ML libraries included. So you host that on a machine with a GPU, and you can actually do inferring in your database, which is really cool, because you don't need to bring any other services, and you can use your Elixir, which is CPU heavy, and have Postgres be GPU heavy. But if you want to have your Elixir machine be GPU heavy, then you can use local NX serving to do that, which is also provided with Torus. But maybe you have your own idea on how you can generate embeddings, and then you have Torus embedding behavior, which you can implement, and then you can do whatever you want. You just receive a string, and then you return a vector. So there is the contract, and you can do whatever you want. And in addition to that, we have Torus Batcher and Torus Nebulex Cache. And these two models are extremely helpful to make the generation of embeddings a little faster. So the pipeline might look like that. You have your request, then you have a read-through cache, then you have a batcher, which will collect a few of the requests, so it's cheaper for you to do the inferring, the embedding generation, and then you pass the batch to your third-party provider. Then it's returned, it's cached, and returned to the client. And once somebody asks again for the same embedding, you will return from the cache, which is the way it is supposed to work. So this is the ideal pipeline. And also, you don't need to remember anything I've told you just now. You can read that in Torus documentation. You have a guide on how to set up reliable and resilient semantic search and how to add that to your application in Torus semantic search. One key point about actually having search in your app is for it to be fast, because we all love when search is fast and it feels really smooth, because it adds the cool touch to your app and your application just feels faster. So every function in Torus library contains a documentation section on how to optimize your search. So most of the time, you would need to, first, pre-filter the results by either applying some business rules, so you scope the query, the results of the query, to only the things that you need, and you only then apply the search. Also, you can pre-filter by using some advanced techniques related to the search method you're using. Like for full-text search, you can easily, I think for similarity search, you can easily pre-filter the results because Postgres stores the data in a specific way. Also, you can add indexes, and every search type has specified what indexes can help and how they can help. You can prefer faster terms because some terms are slower, sometimes are fast, some are faster. For example, prefix searching is usually really fast, and suffix searching is not, because again of the way data is stored and traversed. And yeah, so again, you don't need to remember anything. Everything is in Torus documentation. And quick demo on how this works. Let me show you. A quick demo. Oh, you can see my screen now. Yeah, so there is this application where what we can do, so the first thing that is happening here when you load the page is your model is loaded, like embedding model, the thing that generates embeddings for you, is loaded to the client. So whenever I type something here, I'm using my local embedding model to generate the embedding vector. I'm sending this embedding vector, so this is live view. I'm sending this to the server. Then the server takes this embedding vector, creates a PG vector from this, and inserts that into the query and queries the data. So here, I could say that, for example, I want to find something. What do we want to find? Something with nodes. So group my memos. We have the code for that. And you see, it found a post which don't have either group or memos. So this is the only instance of that word. And memo is a node, group is probably node-taking system. So this body was matched by how close the vectors are of the embeddings. And we can see the generated query for that research. We can also toggle and try different search types. For example, we can change the way we compare the vectors. We calculate the distance between these two vectors by using, for example, L1 distance or max inner product. And you can see actually the variables being injected. So we can see live what was changed, and we can configure that. But you might be wondering what search controls do. So in search controls, we can choose and play with every option that I've shown you before, every search type. So for example, for full text search, we can search by words. So here, let's say, learn common strategies. Learn common strategies. Will this work? Yeah, I think, yeah, it worked. And it excluded other results because they did not match at all. And we can see the query that was generated. Again, a single line of code, post, full text search. It passed title and body, passed our term, and a few options. And these are actually default options, but they are copied from the left bar, so we don't need to div them every time. So this is how full text search works. And for example, you can also use some primitive searches like search. And there, for example, we want to find effective, not effective, but lessons, let's say lessons. And search everything. Okay, it doesn't work. Oh, I know why it doesn't work. Because lesson starts with a capital, and does not treat capitals well. Because it actually is not, how to say that? Yeah, so capitals and the other ones are not compared together. Case sensitivity, yeah, thank you very much. Actually, it is written here. So lessons, so this should work now. Yeah, lessons learned from shipping products too early. I think that should be it. I think, yeah. Let's come back to our previous view. Yeah, dziękuję. To wszystko. Thank you very much.